Okay, and we're going to talk about quickly two extensions of this model that we're going to use. And we don't necessarily need to know these things, but it's kind of interesting to know how this thing actually functions when we get into more complex data sets, because we're never going to get data like this. All right, we're never going to get some data that's so clear, it's two-dimensional and so clearly divisible. So there's two ways that support vector machines are extended to deal with non-divisible data. The first one is nonlinear classification. So you can see this data in the plane again, right? There's no single line that would split the red and the blue dots. And a technique that's used in support vector machines is you actually take that two-dimensional data and you introduce other parameters to project it into a higher dimensional space where it is separable. So in this higher dimensional space, there is this plane that divides them. And then you reproject the data back into its dimensional space, and you take the plane with it, and that plane basically becomes a more complex curve. Super abstract, high dimensional stuff, but you'll see how this works. Basically, it's the way that we can go from a straight line to a curve, right? But this is the overfitting problem. If these points are everywhere and the curve becomes super crazy, then there's an issue. It might just represent that specific data set. When we add other data that we want to train on, it's not going to fit exactly that crazy curve. Okay, and there's specific methods in support vector machines to tune that complexity. So you can go from a straight line to something that gets really crazy. And then the other adaptation is we look at soft margins. So instead of hard division where each point that is misclassified is counted as an error, with a soft margin you have a little bit of leeway. And in this case you have this division and you have this margin, this is a soft margin, where actually every point within this margin isn't looked at as far as performance goes. Okay, so this is a good way to model fuzzy data. Okay, so we want some kind of division. I mean, clearly they're divided, but we don't want to be so strict where like every single point has to meet the line, right? Because some points might be errors, like you counted it wrong or you recorded it wrong or whatever. So we just want the general. And this is part of the parameters now that we can tweak, right? That soft margin is literally, we can specify how big that is while we're tweaking our models. This is just one example of what you might see is like a model visualized. So this is a decision boundary, this purple line, of a SVM that's trained on this messy, noisy data set using both nonlinear margin, right? So this is a curve that's in some higher dimensional space, a plane, but then it's projected down. And then the fuzzy margin, where I don't know if you can see this, but some of these points that are lighter actually aren't considered in the model. This is the margin here, the first isoline, and the points that are circled are the support vectors. These are the points that the model is looking at to define that boundary. So in some higher dimensional space, it's literally a plane with a margin. And it's not looking at these points at all. This point where everything's mixing together is just thrown out of the model.